Swayam Prabha. Digital India. Educated India.
So students, today I will take one more tutorial. Here, see, you already seen, you have seen the last classes also, while I was discussing the many problems. That time I am bringing some more concept, because during the class while I was teaching you, that time maybe it was not the right time to tell you everything in the same time, because see, in a one biosensor there is lots of things, right? There's so many optimizations, so many fabrications, so many mechanisms, so many concepts I cannot tell you at a time. But now it is the right time to tell you everything on a single sensor, right? So that's why this tutorial can help you to bring all the concept whatever I taught on a single slide. And during this tutorial also, that's why I can bring some more concept, more optimizations, so new concept also, that will be very much useful. That's why this tutorial. Let's follow. So in this slide you can see that limit of detection calculation that I will taught you. So let's show you first the questions. So this kind of questions may come during the exam. This is just for your preparations of your exam. Then I will discuss many factors all together, so that you can think a new design for biosensors. Okay, so let's come first for your exam. Calculate the limit of detection. So this kind of questions may come. How you can calculate the limit of detections means LOD, limit of detections. See, I will provide these two images. One is the concentration and second is the calibrations. Or sometime maybe I can ask, there is no calibration curve, maybe this curve will not be provided, only concentration curve. So you have to prepare a calibration curve. So you know, right, how to prepare a calibration curve. Let's summarize. So if I provide you a concentration data and if I ask you make a calibration curve, then so this concentration data, because you can see this is a charge versus time, so this is what? This is chrono kilogram, right? Chrono kilogram, and the technique is called chronocoulometry, right? CC, chronocoulometry. So at a fixed time you have to measure all the current. So here you can see the calibration curve I decided 100 second. So see, this is the 100 second. So in the 100 second you have to measure all the current. So if you have like this one, just this is the zero data. Serum means just zero, there is no target. 10 picogram per ml, 100 picogram, then 1 nanogram, 10 nanogram, 100 nanogram per ml, different concentration, then we increase. So and then you have to, like in the 100, how much current you are getting. So like this way you have to calculate. This is the current. So from here you have to calculate all the current, and that all the current you have to plot in a graph with respect to your concentrations of the target. So in this case your target name is PSA, prostate specific antigen, right? PSA is your target. So in the x-axis you can plot concentration of PSA, unit is gram per ml. So without unit diagram is meaningless. So always add the unit, right? Here also charge microcoulomb, right? So in this concentration this much charge we got from the diagram 1. Then this is 1 2 3 4 5 6 concentration there, right? So the 6 concentrations we actually plot all the current, and you can see this is the error bar, right? This much error bar we are getting. So error bar means at least you have to collect three data, three data in a same concentration. to get this error bar, at least 3. So, like if you have like 10 picogram, let us collect 3 data, but in this diagram there is no 3, there is 3 data not available. If I put all the 3 data, it will be too much hazardous, you cannot find out the data. That is why I just showed you, I have showed just only 1 1 1 1 like chronokilogram. So, if I ask the calibration, make the calibration plot with this diagram, then you will not have the scope to use this error bar. But if I show you, but if I provide you like different concentration, like this is the like 10 picogram data and with 3 concentration, this is 10 picogram per ml, then this is the 100 picogram per ml. So, you will have 3 data, then you have to collect the standard deviation. So, in each concentration actually you are getting this much variation, that standard deviation you have to put it here, clear. Now, let us come to the limit of detection calculations. So, before the limit of detection calculations, I think I already taught you that you have to collect the standard deviations of your 0 data. 0 data means without any target data, that is the 0 data. So, your 0 data is like just the female serum, like just serum, there is no prostate specific antigen. Okay. So, in this case, suppose your 0 data SD means standard deviation is 0.35. Then you have to multiply 0.35 into 3, right, 3 times standard deviation. You can remember 3 SD value. That value means, right, 1.05. So, 1.05 microcoulomb is your 0 data standard deviation, 3 times standard deviation. So, that much current you have to consider just like a 3 times standard deviation value. And after this 3 times standard deviation value will be your considerable detections for the biosensors. Otherwise, if say suppose your this, so suppose this one, your 3 times standard deviations may come here. If your 3 times standard deviation may come here, although you did, so this is the 3 SD for example, although you got 1 2 3 this concentration data, you can detect, but at their below of the 3 times standard deviation. So, this concentration, this data is the meaningless with your biosensors. You cannot show them, you cannot tell them this is your limit of detections. Your limit of detections you have to, so with this concentration, so you have to draw a straight line with this all the concentrations and this intercept, this one will be your limit of detections. This intercept, although your sensor can detect these 3 concentrations also, these three can detect, but they are below of this 3 times standard deviation, so they will be useless. This data will not be considered for your with sensitivity of your sensor. So, your sensor is not that much sensitive. So, if you want to make your sensor very sensitive, then your standard deviation should be very low. If like once you are developing 3 sensors, if their data like chronokilogram data, if they are very close to each other, then your sensor is really reliable because their deviation is very low. But if you are getting like one same concentration, one is here, one is here, one is here, means large deviation, then your sensor is not that much reliable because they are not reproducible. So, reproducibility can decide your, if your standard deviation is very low, then you are very much reproducible. Very high means not reproducible your biosensors. So, like this way you can calculate your limit of detections and you can predict your sensor sensitivity. See, in this case, if your 3 times standard deviation come here, all the concentration here, then your detection limit around nanogram per ml, right? LOD close to something nanogram, like 10 nanogram per ml. So, your sensor will not be considered as ultra sensitive. But if you can detect your sensor with some femtogram per ml, very low, and with 3 times standard deviations like this SD value will be, its position is like this, like your femtogram per ml is just above of this line, you can say that your biosensor can detect very low analyte concentration. So, your sensor will be considered as a ultra sensitive then, or it is called highly sensitive. So, your limit of detection can guide you. Okay. So, like this way you can calculate the limit of detections that I showed you. And another thing, just try to remember, just I showed, because limit of detections calculation is very important parameter for the biosensor device. Just I am summarizing here. So, first you have to like collect different concentration data, like 0, like here target concentration 1, target concentration 2, target concentration 3, target concentration 4, and each concentration at least 3 data you have to collect, each concentration, then get their standard deviation value, each concentration get their standard deviation value. And for calculations of LOD, limit of detections, you have to multiply with 3 with the standard deviation of 3, then that 3 SD you have to draw. Now, T1, T2, T3 all the concentration, suppose your 0 data, right, your 0 data here, you are getting your 0 data here, and your target concentration, but 3 times standard deviation here, your target concentration T1 suppose here, T2 you are getting here, T3 you are getting here, T4 here. So, they are the standard deviation, SD value, like all the standard deviation you have collected. See, although your 0 data here and second, this one 0 data and second concentration data also more than 0 data, but this one will not be considered with your biosensor, means your biosensor is not that much sensitive because your 3 SD value just above of these concentrations. Then you have to just draw the straight line, then because this one your limit of detection. Clear? So, like this way you can determine the sensitivity of the biosensor. Now, the next questions. In this tutorial, I will show you like describe the optimizations of immunosensing conditions. I think many times I taught you the optimization technique for the biosensors. Like always I am saying that you have to optimize the applied potential, right? Because so if you apply very high potentials, maybe in that case some interference species they can oxidize, right? So, you have to apply in such positions, so the interference species should not be oxidized. So, optimization potential is important, chemical optimization, their concentration is important, time, how long incubations you are using, as I told you, suppose ECC redox cycling, right? ECC redox cycling case A plus B plus C, 3 chemicals you are using. So, maybe you have to incubate it for 10 minutes or maybe 15 minutes or maybe 50 minutes. So, which time you want to use for this reaction incubations, that also you have to optimize, right? So, this kind of questions may come, that from the optimizations of immunosensing, which conditions you have to optimize and how to optimize. See, here this kind of diagram I can give you the exam 1, 2 and 3, and you have to mention, see I already put the answer, like this is the applied potential region where I got the very good data, that is the applied potential optimized data. So, and optimized concentration data, that everything we decided. Let us show you why we decided this one is the optimized conditions. So, first See here, number 1 curve is the PBS plus FC means ferrocene. So only ferrocene, this CB is the only ferrocene. Now number 2, this one is the ferrocene in the serum sample. Means if you want to use the real serum, real sample like serum, and if your ferrocene means your electron meter inside this serum, they may behave differently, right? So because there is some other species can interfere. So that's why you have to collect the actual cyclic voltage in the real serum sample, because you are using the, you are not diluting, just real serum sample you are drop casting inside a biosensor, that is the biosensor, and like this is the real serum sample. Then you have to check your ferrocene how it behaves. You see the behavior actually change. That's why during the optimization process you have to think like the other mediator, other like chemicals you are using, how they are behaving in the real sample, not only the PBS, in the real samples also. That is also kind of optimization process you have to check. Then see to an AOX. AOX means ascorbate oxidase. Generally you can remember in the real sample it may contain ascorbic acid, right? Ascorbic acid. So ascorbic acid is really interfering species, it can be oxidized easily in the lower applied potential. So you have to remove this. How you can remove? You can add some ascorbate oxidase and you can remove the ascorbic acid. And let's see the cyclic voltammogram after adding the ascorbic acid. It can help you like which concentration of ascorbate oxidase you want to use, how long you want to react with ascorbic acid, ascorbic acid plus ascorbate oxidase, right? So you have to check the time, how long they can react each other, and maybe all the ascorbic acid can be removed by the ascorbate oxidase. That also you have to check. Then only serum sample, you can collect a cyclic voltammogram, only the serum sample, how it looks like. So it is showing, see, it is almost like it start the oxidations from here. It means ascorbic acids may contain many species that start the oxidation from this region. So you should not use the applied potential more than this, because from here only you can see the interference species oxidations can start, right? These things only you can decide if you can measure all the cyclic voltammogram before before final decisions. Like once your biosensors are ready, well, like fabrications of antibody, your chemicals already selected, everything done. But before that you should have this all the informations. Then only you can decide like which potential you want to apply. So applied potential region, it is the best area if you can use. Which position you should use for the application of potential? From the cyclic voltammogram, I think it is already very clear. See, this position is the best positions. Otherwise, see when the serum present, see the oxidation actually starting from here with serum. So it is better in this region, almost there is no contributions from the interference species. That's why let's try the potential optimizations. So you can try the potential optimization at 0.09 volt in this region, 0.09, 0.13, 0.17, 0.21, 0.25. Like as we thought that this region is the best region, so let's check few potential and let's check the signal to background ratio. If you suppose you want to use the glucose, ferrocene and glucose oxidase, so this reactions you want to use. So you know, like I already taught you like what is the signal corresponds to, what is the background corresponds to. So if signal, the chemicals you have to collect, that implies the signal, and and you have to select the chemicals that implies the background. Those chemicals are selected and then collect the signal to background ratio. And from there you have to decide, which potential is showing highest signal to background ratio. So here you can see 5.4, 7.2, 4.5, 3.1 and 3.8. So 7.2 is the best. So 0.13 is the best. So 0.13 potential you can select for your biosensors. So from now onwards, then when we will design these reactions biosensors, this biosensor, then always you have to apply 0.13 volt. because this is the best potential, you are getting best signal to background ratio. Now one thing you can consider, like the concentrations of the ferrocene. So concentration of ferrocenes may play a very crucial role. So this is the mediator. So sometimes these mediator concentrations can vary your signal to background ratio. Let's check which concentration is the best. So you can try different concentrations of ferrocene, like 1 micromolar, this is the micromolar unit, 10 micromolar, 100 micromolar, 1000 micromolar, different concentration of ferrocene you can try, and let's check the signal to background ratio. So you got the signal to background ratio 2.12, 3.69, 7.23 and 4.63. So 7.23 is the best. So this is the optimum ferrocene concentrations. Like this way you can optimize each parameter. In ECC redox cycling there is lots of parameter, like you may have to optimize like all the reagent concentration, then you have to think about the optimizations of like applied potential, everything you can optimize like this way. Now let's come the optimizations of immunosensing conditions with time. See, this is also very important factor, because your biosensor is the immunosensor, right? Immunosensor. In this case you have to be little bit careful. You have to optimize your incubation time. Incubation time. What is incubation? Because your biosensor ready for the detection, primary antibody coated, like this is the sensor, while and you add the target, your target already bound, and your secondary antibody that is already labeled, right? This is labeled, this is labeled, this is labeled, right? So you add on the primary, this is the primary antibody, antibody 1, and this one secondary antibody, antibody 2. Now on the primary antibody coated surface, when you drop like say target and secondary antibody mixture on this surface, antigen antibody binding. So this is the antigen here, sandwich, some sandwich forming, no? So antigen antibody binding is forming. So it is some slow reactions, antigen antibody binding. So this antigen antibody binding may take some time. These incubations, that is you have to optimize. Maybe it may take 5 minutes, 10 minutes, 15, 20, 25, 30 minutes. In different time interval, you can check their binding effect. How you can check? You can check with this signal to background ratio, something like this. Right? In this, after 15 minutes, how much signal to background ratio you are getting? After 50 minutes, then 30 minutes, 50 minutes, 1 hour, like this, you just check it. Then we can plot, like with standard deviations, you can plot like how much current variations you are getting. See, you can see almost after 10 minutes they are almost saturated, right? So after 10 minutes, 10, 20, 30, they are almost saturated. Then no need to consider the high, long incubations. So 10 minutes can be the optimum incubation time. This is the optimum incubation for your biosensor. So like this way you can optimize the time. So let's summarize, like why you need the optimizations, because there is an antigen antibody binding. For that you need some incubations, because this is not so rapid, like just drop and check, not like glucose. So glucose case it is one thing, like if you have glucose oxidase and if you add the glucose, like glucometer, you know, within a few seconds it can give you the data. But for the immunosensor case, you have to incubate your sensor after adding your sample that may contain with target and your secondary antibody. For that, this incubation time help you to bind this antigen antibody. Also, if you are using like redox cycling, suppose you are using here suppose electrochemical chemical redox cycling. So in for that you are using some chemical, right? So you are using some ferrocene, that is oxidizing ferrocene plus, oxidizing ferrocene plus, and then ferrocene plus again reduced back. For that maybe you are using with the help of some glucose oxidase. So maybe you can use some glucose. So means ferrocene is oxidized on the surface, and that glucose actually you are trying. So for this kind of, this is the enzymatic, this is EN redox cycling, and EC redox, if you want to EC redox cycling, there is no enzyme. Without enzyme you can try, like electrochemical and chemical. So for that reactions also you may need some time, because for these reactions may not happen immediately, or it may happen immediately, but if you incubate it for some time, like 5 minutes or 10 minutes, maybe you may get the very high current. Your signal to background ratio will be much higher than if you check immediately. Then let's incubate for some time. That incubations also you can optimize. Okay. So this all the things you have to consider while you are developing a biosensor. So in this tutorial I just asked the questions like this way, like describe the optimizations of immunosensing conditions. So you have to describe like how they are behaving. First you have to measure the cyclic voltammetry for your ECC redox cycling. So like just without reagent you may get one cyclic voltammogram. After adding one reagent you may get like different cyclic voltammogram. When you add all the reagent for ECC redox cycling, you may get the amplification. That cyclic voltammogram you can see, right? Then from that cyclic voltammogram you can predict. Let's take one more cyclic voltammogram with some real sample, because finally anyway you are going to use a real sample, and in that real sample this all the chemicals behave same, or maybe there is some change, that you can check. Then you can decide based on the cyclic voltammogram which area actually is the best area for the measurement. Suppose in this case you can see in this area actually there is not much interfering species effect. Accordingly you just optimize, right? Like this way you can explain your optimization of the biosensor. Clear? Then again the next questions come, and that is very important questions for your biosensing study. That is in the exam also may come this kind of question. The washing process why required? I think the last time also I told that washing process always required to eliminate the interfering species effect, right? Eliminate interfering species effect. But this washing process is not always possible if you want to develop a point of care testing device, because this course is a point of care development, some device. But washing layman they can't do on site. So you have to develop some washing free biosensors, that I already taught you. So how you can develop the washing free biosensor? That is proximity dependent, right? Proximity dependent. Proximity dependent. I think you can remember, like on the sensor surface we can develop the redox cycling, right? So if this redox cycling happen very close to the surface, then you will get the higher current, and if this redox cycling happen far from the surface, if it is far, then the reaction rate will be slow, then you will get the lower current. So that washing free concept you have to discuss. And so washing process always required to eliminate the interfering species effect, but we can design a washing free sensor based on proximity effect. At that time you have to be very much careful that although you are not using the elimination of interfering species effect, but they should not contribute much on your background current, otherwise your signal to background ratio will be low. Means that you can minimize, because see in your washing free sensor case you have lots of interfering species present, so your application potential is really important role that you have to mainly consider for the washing free biosensor. Application potential, proximity dependent effect, that you have to consider. How fast this proximity dependent effect is possible, that you have to consider. Clear? So how we can make the washing free biosensor? That proximity dependent biosensor you have to explain properly, that I taught you already. Okay. So, the conclusions today, all the tutorial that I told you, that let's think about like limit of detections, how to calculate. Let's think about the optimizations of the biosensors, like all the steps, like potential optimization is very crucial factor. Then concentration optimization, concentration optimization, that is a very important factor. And always you have to try the real sample. So always think how to handle the real sample on your sensor surface. Then immediately once you fabricate your sensor, try real sample and let's check your all the chemicals, all the potential that you have optimized there, that you can validate with real sample or not. If your biosensor cannot validate the real sample, then no use. So always you have to try the real sample. Okay. So that's all for today's tutorial. The next tutorial again I will discuss few more concepts, few more discussions on the this kind of new like technology also I will bring slowly based on these discussions that I already taught until now all the classes, and you may think independently. That's all. Thank you.